Okay, so the idea is that we want to add long-term memory. We want to add some way of easily just storing information in an RNN that will maintain over time. Right, if you think about an RNN, we've got H coming in, it gets manipulated, we've got H coming out, right? So this is H sub I minus 1, and this is H sub I. And this is our only form of memory. And if we remember, we have a transformation that happens. We calculate the new H based on the old H, based on the incoming X. We add a bias, we apply an activation function. The idea for a LSTM, and LSTM stands for long short-term memory. So the idea is that it can maintain both long-term and short-term memory. Invented actually quite a while ago. So this was actually invented back in, I think it was 98. So in terms of neural networks and deep learning, that probably was a long time ago. So what we're going to add in is we're going to add in, as well as H, we're going to add in C. So C is going to be long-term memory, and H is going to be short-term memory. So this guy is going to be short-term, and this guy is going to be long-term. And we're going to see that there are some mechanisms that make it very easy for C to just sort of be maintained from state I minus 1, time step I minus 1 to time step I. We're going to have mechanisms to put values into C, have some mechanisms for maintaining C state from time step to time step, and also mechanisms for forgetting or clearing C, resetting, writing to C, and also reading information from C. That's what we're going to need to be able to do. Let me show you a diagram. So this is our RNN. We've got X coming in, X sub I coming in. We have H sub I coming in, C sub I coming in. By the way, I'm going to be providing you some formulae. Now's probably a good time to go get those. It's actually on Wednesday's schedule. It says gated recurrent units handout. So that's a good thing to have for two reasons. One, I don't want you to have to be writing down these formulae. And also, when I write them down, I want you to double check and make sure that I am not writing them incorrectly. We know this goes through a weight matrix. This goes through a weight matrix. These get added together. This goes through a activation function. And normally, of course, what happens is that this becomes the output of H, and this gets fed up into Y. It's slightly different here. So what's going to actually happen is we're going to go ahead and make this activation function be 10H. The second thing that we're going to do is we're going to actually add a gate here. So think of this as a gate that either can pass through C sub I or not pass through C sub I. And this is called the forget gate. So we're going to have 3 gates. Forget is our first gate. So if this gate is open, C sub I is not going to feed in to the new time step. So what that has the effect of doing is forgetting the old value of C sub I. Okay, so this will go on, and we'll have a plus here, and then we're going to have another gate, which is our I gate, or our input gate. So this controls whether this new calculation that we're doing here, so how we used to calculate H, actually feeds in to calculating our new C. So this becomes our output, C sub I plus 1. So we have, let me back up just a second. What we're trying to do is come up with a mechanism for C to maintain its state easily from step I to step I plus 1. or let's use the correct terminology here. So x sub I is coming in. We've got y hat sub I coming out. We've got c sub I minus 1 coming in, h sub I minus 1 coming in. And we're going to have c sub I and h sub I coming out. So the forget gate is going to allow us basically, if we open the input gate and close the forget gate, then we've got c sub I minus 1 just passes directly on through and becomes c sub I. So if the forget gate is 1, which means closed, and the input gate is 0, which means open, this means c sub I equals c sub I minus 1. Questions on that? Does it make sense? So close this gate, open this gate, we just pass it straight on through. We haven't seen where h sub I comes through, but that just shows us how c sub I minus 1 could do that.
It makes sense.
It makes sense. Okay, thank you. If, on the other hand, we open the forget gate and close the input gate, then c sub I is now coming in this new computation. So basically what happens is we can make our new c sub I either be completely the c sub I minus 1, or we can make it be this new computation. Or if we close both gates, we actually can combine them together. And finally, we need to figure out how do we calculate h sub I. So h sub I comes from our previous c sub I. So what happens is we have another gate. I'm going to just put some arrows here to make sure we understand the direction things are going. So this is the output gate. So we have a forget gate, an input gate, and an output gate. So h sub I minus 1 comes in here, gets combined with x. We do our matrix multiply, we add our bias, we come through, and we may or may not go into C. The old C sub I may or may not come into the new C. And then the new C may or may not come into the H. Now, a couple things about this. What is the size of h sub I minus 1?
I am here. The size of h sub I minus 1. Well, it has to share dimension. I don't
What's the
recall.
first dimension? Like the first dimension of x and the first dimension of y is also the first dimension of h, which is?
The batch size?
Yeah, so this is going to be batch size by
some L, it's like our hidden size.
Yeah, let's just say some hidden size. We make it as big as we want, right? And each of these are independent of one another, right? We're independently kind of going through this weight matrix and adding in our x, and so they can be storing different sorts of things, right?
Mhm.
Same thing is true for C. So C is going to be batch size times, well, how big is this going to be actually? Let's continue this conversation, Emmy.
Trying to think of why it wouldn't also be the hidden size.
Let's look at this plus here.
Uh-huh.
So if we're adding together this guy, which is batch size times hidden size, this guy had better be
Also batch size times hidden size.
One thing I want you to know about these gates, they are not all or nothing. It is to not apply to all of the hidden size, okay? Instead, it applies one by one by one. So every item in here, in H, independently gets its own value of forget, input, and output. So for example, you might have 3 entries. Let's just forget the batch size for a moment. So you have 3 things you're remembering in here, in C. One of them may go straight through, and you get, so the input gate may be open and the forget gate may be closed. A second one may be the converse, and a third one may be both of them are closed. Okay. Same thing is true for the output gate, is that it can be different for all of them. So we're going to look, and I'm going to show you how you can compute the forget, the value of the forget, the input, and the output gate independently for each input. sorry, independently for each one of these values. There's a question?
I have a question. I get the purpose of the forgetting input gates, but what is the purpose of the output gate? Which one?
The purpose is to let us decide whether stuff from that long-term memory is actually, I guess the way I'm going to back up a second. The way I think about it is maybe in some ways it provides us a way to clear out our short-term memory as well. Okay. So to just choose to have long-term memory that's coming out here, but not feeding into the short-term memory. Right? If we want the contents of the long and the short-term memory to be different, then we need a way to ensure that they are not identical. And that's why we have the output gate there. Does that help?
Yeah, so it seems that the output gate is meant to weight the hidden matrix time. But it's meant to weight the product of like the next WHH times H, right?
Weighting it in some sense, yes. So you may be getting to a part of this where these gates are not either all open or all closed. They can actually be partially open and partially closed. Is that what you mean by weighting?
Okay, yeah, I think I understand.
Okay. So let's look at one of these gates. Let's look at, let's say, the forget gate. Okay, so we're going to say the forget gate at time t is going to be a sigmoid, and it's going to be sigmoid. That's how we're going to get a value between 0 and 1. So that's this foreshadowing of the fact that the forget gate is not either completely open or completely closed, but is some partial amount open and closed. So it controls how much of Ci minus 1 goes through to be part of Ci. So what information might we want to use to decide whether we want to copy this old hidden state?
Probably x sub I.
X sub I sounds good to me. So let's take x sub I and let's multiply it by a weight matrix. What do you want to call it, Aditya?
Some forget, so wait, x forgets, so xf.
XF sounds good to me, right? So this is the weights specifically for helping us to determine for the x sub I whether we're forgetting or not. And notice the number of columns in W is going to be the size of F, which is going to be basically this hidden size. So we can, for a given x sub I, have different weights for different columns. So we can get this f of t is a vector. And so we may have some of them on, some of them off, some of them higher, some of them lower, and so on. Okay, what else do we want to use? As well as the x sub I input is going to control, is going to be used to help determine what the value of this f is going to be.
HT minus 1.
Sure, we want to also take in our old h. I'm just looking to myself and thinking, why do I have t and I both? So let's switch this to t, and this will be h sub t minus 1. And then what sort of matrix do we want to use? That was Yuki, right?
Yeah, like WHF.
WHF sounds good to me. Plus?
A bias.
Sounds good to me. We'll call it B sub F. So this gives us all the information we already have at our disposal to determine whether we want, I suppose we could take in the old C, could be a possibility, but we're not doing that. So we'll take in the X, we'll take in the H, we'll combine them together, we'll throw in a bias. We're not using actually these matrices, we're using different matrices, and then that'll give us our decision of whether this gate is open or not. And again, it's a vector of gates open or not for each one of the components of C sub I. So we might have, if our hidden size is 5, f sub t might be equal, 0.3, 0.99, and 0.5. So we've got a gate that's more open than closed, a gate that's, let's see, sorry, and the other thing to keep in mind is 1 means closed for all these gates. So this one is almost completely closed, half open, half closed, more open than closed.
I don't understand the intuition why if xt and so if you have the same x input and h input, the h should be forgetting the same amount.
We have the same x and h. Can you repeat that again, Daniel?
So according to the formula, if you have the same x and h in like two things, then you should be getting the same amount.
So if you have the same x and h, and then I didn't follow the rest of it, you would cut in and out.
Then you would be forgetting the same amount.
If you have the same x and the same h, you'd have the same setting for the forget state, exactly.
Yeah, but what
Keep
is
in
the
mind that
intuition?
well, the
Like, why
h
do you want
contains
the-
all the information of your previous sequence. So this contains all the information from x1 to x sub t. I suppose I should just change these all to t's to match over here. So the only information there is all of our inputs that we've seen so far, right? Our sequence of inputs. This captures our entire sequence of inputs we've seen so far. So theoretically, should be enough to help us decide what to do at this point. Does that help or not?
It's because if we're trying to use like all our inputs to determine the variable f, then why don't we use like c also?
Yeah, I mean, it would seem reasonable to include C, although when you think of it, well, so H is some proportion of C, right? I think you could. I don't see a reason why not. But I don't know, I don't have a good sense of why it is that they chose not to have a C in here as well. Part of it may just be having, more parameters.
Okay.
So then we have our other 3 gates. Right? So our other 3 gates are I and O, and they all look basically the same. And what I'm adding in here now is, this is WXO plus H2 minus 1 WHO plus BO, and this is BI, WHI, WXI. So we've added in basically another 6 weight matrices in order to compute the values of these 3 gates. Actually, there is one thing still missing from this diagram, and that is what happens to y hat sub I. And y hat sub I, we have to kind of go around here, is still computed from h sub t.
I could ask a quick question.
Go ahead.
So sorry, just to clarify, those 3, the matrices like XF, XI, XO, those are all new weight matrices that aren't shown in the diagram at the moment, right?
That's true. They're not shown in the diagram. They are used to calculate these values of F, I, and O.
Okay, cool. Thank you.
And again, as a reminder, they're all vectors. So what's going along these paths are vectors of size, let's just say hidden size for the moment, okay? Hidden size. And so we got a vector of size hidden size here, and it hits this gate, and this gate is a vector as well. So one component may go through, the other component may not go through, and so on.
Okay, cool.
Okay.
So I did some quick Googling, and there seems to be a variant that does the.
Uses the C as a variant. That seems quite reasonable. Sure. Okay, so why does this work in some sense? Why does this work in actually allowing you how to have long-term memory? Well, from the forward pass approach, the way it works is you can again have the I gate off and the F gate on and just pass through data, right? From time step to time step to time step. For some, again, I'm looking at some particular element of this vector. For example, let's say you are looking at, let's look at Wikipedia. So Wikipedia has its references inside double square brackets. Okay, so this is some Wikipedia reference. If you were a language model for Wikipedia, you might have different stuff inside a wiki reference than outside the reference, right? There's probably some format in here. There's probably a URL, for example, some other sort of stuff. So you might want to keep track of whether you're inside these double square brackets or not. So you could imagine one component of this long-term memory here might keep track of, I'm inside double square brackets. And this wiki reference may be long, right? This is a short one that's 8 characters, but you might have a reference that's 100 characters long or 150 characters long. And so this allows us still to maintain this by ensuring that this particular component of the long-term memory will just pass through and is not going to get updated by this H and this W. Now, in what circumstance might you want to update this? Right? To say we're no longer inside double square brackets. Well, probably after this double square bracket, right? So maybe you're going to have, let's say this is a token, and this is a token. So you might have an X coming in with a right square bracket. And if it's the first right square bracket, maybe we don't do anything. We don't open up the I gate, we don't close the I gate. We leave the F gate open. But on the second square bracket, we want to do something different. How do we keep track of the fact that we've seen a second square bracket in a row? Right? If we're not going to use the long-term memory, we would use the short-term memory. Come in here, well, I guess we would be using different slot in C, which would get put into H for the short-term memory. So we'd have a long-term memory that says I'm in the middle of double square brackets, and a short-term memory that says I just saw a square bracket. Then when we see our next square bracket, we can go ahead and say, okay, I know I just saw a square bracket. I'm seeing a new square bracket. Oh my goodness, I need to go ahead and update that particular field in here. I want to reset it. That is, I want to open the forget gate so we forget it, close the input gate so I can write something to it. Does that concept make sense for the forward pass? How it can just keep maintaining it. So the fact that we can maintain it is one thing, but how do we train it? How do we train somehow an error so that we can say when we find the second square bracket, go into double square bracket mode? Right? This may be a very long way. That is a huge number of time steps down. And we need to go back and update in huge time steps. So let me unroll this LSTM. Before I do that, let me actually show you the remainder of the equations, which is very small, but I showed you the equations for the forget gate. I've given you a diagram of how we're computing C sub t and H sub t, but I didn't actually show you the formula. So we are basically going to say that C sub t is going to equal, well, we're going to combine together C sub t minus 1 and F. So we're going to take basically F sub t, right? And then we multiply that element-wise by C sub t minus 1. And then we'll add in the I sub t Hadamard product with this computation, right? So that's tan H times X sub t W X sub, I could call it H, or I could call it, let's just call it H since that's what we used to call it. So X sub t WXH plus H sub t minus 1 WHH plus B sub H. Okay, so that's our C sub t. This whole computation is something we've done before. And then H sub t equals how much the C sub t do we want? Whatever our output gate is, Hadamard product with C sub t. So that is the let's make this so you can read it. Okay. That's just this the remainder of this diagram. Any questions on this formula? These formulas? All right, so I am going to now look at back propagation. And in particular, I'm going to do that by unrolling this RNN a bit. So we have got our LSTM. And this is at various time steps. Let's say that we have a y hat coming. So this is all the LSTM, right? We have a y hat coming out of here. Okay, so this is y hat sub L for our sequence length. And this then, of course, goes into our loss. If we are computing the loss from all the intermediate y sub hats, then it's pretty easy to push back loss, right? Because if we are here and we're looking at a particular weight matrix of either the XH or the HH or the HY or these new ones, right? XF, HF, XOHO, XIHI, then if we are computing the loss from all these intermediate y hats, then we have a path directly from here down into here. So that's a very direct path, and we can easily push gradient. We can also probably push gradient pretty reasonably into this time step and then back across here. The problem comes about if our computation is just at our last y hat. Because if we're at our last y hat, we have got long paths back to, let's say, these weights here. And what do we know happens in long paths?
We either have vanishing gradient or like exploding gradient.
Yeah, so long paths often lead to vanishing or exploding gradient. Have we seen an example of a neural net where we had long paths and yet we did not have vanishing gradient?
Residual neural networks.
Residual neural networks, right? The key, we had these shortcuts, And these shortcuts had the characteristic that their derivative was 1. And so therefore, you could follow as many of those shortcuts as you wanted to get back and push your gradient, push your error back to early stages, early layers. That's the same sort of thing that we can do with our C sub t. We know that if we're going through H sub t, if we look at just a regular RNN and you go through H sub t, we know that in order to get from H sub t to H sub t minus 1, that we have to go through a WHH matrix, right? And if we go through that WHH matrix multiple times, right, because we're going the forward pass as you go from H sub t minus 1 to H sub t in a normal RNN, you're going through the WHH matrix. So in order to go back, you need to also go through the WHH matrix. So that causes a problem with possibly having either vanishing or exploding gradients. But if your weight matrix is basically kind of bigger than 1, you can have exploding, and less than 1, you can have vanishing. We're going to still have that problem with our H's, okay? But that's okay, because this is short-term memory. And we're going to fix this by having a path that gets us through the C's, through the long-term memory, with a derivative of 1. And right, the thing to keep in mind for LSTM is if we look at our C sub t minus 1 coming in here, it goes through, and we have a gate here, and then we go through to C sub t. And then we go in here, and we have a gate here. And we have a bunch of stuff that happens here, right? If this gate is open and this gate is closed, what is the relationship between C sub t and C sub t minus 1? So open, closed, what's the relationship between C sub t and C sub t minus 1?
So if C sub t is equal to C sub t minus 1?
Yeah, they're equal.
Yep.
So what's
Yep.
the derivative?
Derivative is 1?
Is 1. So basically, for any element of C, if any element of C has a period of time where it is closed in the forget gate and open in the input gate, we're guaranteed to have a derivative of 1. In fact, let's even forget about the input gate.
Okay.
Right? Because if we forget about the input gate, we still have a derivative of 1 here, right? So we still have a component. There's a path where we go from C sub t to C sub t minus 1 that has a derivative of 1. So we can go in our back prop from here to here to here as long as this gate is 1 or close to 1. Does that concept make sense?
Yes, but doesn't that mean there's still can be the problem with vanishing gradient, because you still have the input gate to worry about, right? And the input gate by itself can pose vanishing gradient.
So since we can't get to 1, since we can only approach 1, we do have a problem. You know, we could have a value like, you know, 0.99 to the k for some k. And that does, as k gets large, eventually get small. We can still, though, as we're adjusting the gradient, not only be adjusting the gradient of C sub t minus 1, but also be adjusting the gradient of this gate. So maybe over time, this is moving to 0.99, you know, 3 nines to the k, or something like that, or 4 nines to the k. So we have this fight against the vanishing gradient in terms of making the forget gate value larger and larger, closer and closer to 1. And the closer and closer it gets to 1, the less we have the vanishing gradient issue.
Okay, I see.
Let's look at some important takeaways. Okay, so some important takeaways are One would be, we have different components of C and the gates. So one component may have that F gate closed and may be able to push gradient very well back through this path. Another component may have it open, and so we can't push gradient back via C. A second takeaway. So it's easy to push our gradient back if F is close to 1. So what that means is when you are initializing your network, you would like to make it so that you can easily push gradient back. Okay? The network can learn that, you know what, I don't actually want this gradient pushed back. I don't want C sub t minus 1 to feed through to CT. I want to turn that off. But it's much easier to learn to open the gate than it is to close the gate. Because if we open the gate, we can push stuff back very far. If we close the gate, we're stuck and it's much harder to learn. So therefore, we want to initialize such that F is approximately 1. How might we do that? It's really pretty simple. Just set B sub F equal to, let's say 1. Right? It's a vector. We just set it to a vector of 1s. And so when we randomly initialize the weight matrices, we're initializing them to small values such that the totals are normally, between, let's say, -1 and 1, something like that. So we set this to 1s or 2s or something like that, just a small positive number, such that given our random initialization of all the weight matrices, that F will likely start close to 1.
But
Now this
doesn't
is
like
handled.
tan H has a negative chance to negate values as well, right? Like it doesn't just flat out zero.
Yeah, tan H goes from -1 to 1. Yes.
So if there's some negation happening, will that affect it? Or no? Oh, actually, it doesn't affect the F gate.
Right, it's not going to affect the F gate.
Okay, yeah, cool. Not much.
Yeah, because it's not seeing a tan H. How big do we want to make our hidden size? Which also will control how big our long-term memory is too. That's one of these hyperparameters you need to choose. So if you make it too big, you're going to start overfitting. If you make it too small, you'll start underfitting. You want the Goldilocks size.